Hey, how are you doing, guys? I'm Dohan. Here is lesson 9 part 2, so let's get started. In this video, we will delve into ensembling techniques using fastai library and gradient boosting. After that, we will move on to explore Bayesian optimization. So let's get started with our lesson. Let's get started with ensembling. Often for tabular problems, we deal with ensembling from other models. For today, we will look at using XGBoost mixed in with fastai, and you'll notice we will be using fastai to prepare our data. First, we import all from fastai.tabular, and we will be using adults dataset. First, we grab it by using enter_data method, and then we call pandas.readCSV to create our data frame. And as usual, we define our categorical and continuous variables, the preprocessors that we are going to use like categorify, fill missing, and normalize. Then we define our dependent variable, and we are going to use category block as our y block. And lastly, we define our split to be random splitter. Then we build our tabular pandas object by passing it our data frame and all the stuff that we defined in the above cell. Now we will go ahead and use our tabular pandas for gradient boosting. Here we import it. And for gradient boosting, you need your x's and your y's, the raw values. First, we define our x train and y train by calling toTrain. Then we define our x test and y test. And here we make our XGBoosting classifier by setting the number of estimators to be 100, the maximum depth to be 8, the learning rate to be 0.1, and the subsample is 0.5. Now we can fit by calling model.fit and pass it our x train and y train that we defined. And here we grab the raw probabilities from our test set. So here is the probabilities. And we can also check its accuracy by using fastai accuracy function. And here is the accuracy. An XGBoost, random forest, and other are accepting the permutation importance. So XGBoost has the ability to look at the importance from the models. Here we import plot importance from XGBoost. And here is the importance. Now we can call two data loaders. Then build our learner. And fit for 5 epochs, and we get accuracy around 83.84%. Then we grab the predictions. And now let's check to see if our feature importance changed at all or not. So this algorithm I have covered in details in the previous video, the part 1 of this lesson, so you can go and check it. And here's our permutation importance. So our neural network is looking at the data differently than the gradient boosting tree. Now let's perform our ensembling. For this mechanism, we will just take the average. Here we take our neural network predictions and sum it with our gradient boosting predictions and divide it by 2. And here is our averages. Then we are going to apply argmax on it. So here we're just finding the index of the maximum value for each row in the averages. For example, the first value here is 0. So the index of the maximum value for the first row in average is 0. And if we go back and check, As you can see here in the first row, this number here is greater than the second number. Now we can check its accuracy. So this is the accuracy for the neural network, for gradient boosting, and here it is for both of them combined. And as you can see that it's performed a little bit better. Now we can also do it with random forest. Here we import it. Then we define our random forest classifier with 100 estimators. And now we can fit. And when we are doing the feature importance here, we're not gonna use the default random forest. So Terence Parr and others, including Jeremy, did a paper called Beware Default Random Forest Importance. So you can go and check it from here. So we are going to use their package, which is a random forest pump. And here we import it. Here we made our importance. Then we plot it. And as you can see, first we have education number, relationship, age. So this different than the other two models. Then we can grab our predictions. And now let's go ahead and ensample them together. And if we see the accuracy, so it didn't quite work how we wanted to, but that's okay, the goal was to experiment. Now let's go with the second notebook. In this notebook, we will work with Bayesian optimization. So Bayesian optimization is a hyperparameter tuning technique where we give ourselves a grid area to search. So we will try values randomly at first inside this grid search and seeing what values will be working with us. So for example, here we maybe start at 0.1, then go around 0.35, then 0.4, and so on. And we will look how they affected our y's until we find the best possible value for our model. So as we used to do, we will start by installing fastai library and importing tabular module. Then we grab adult sample dataset. And here we import Bayesian optimization. So to work with Bayesian optimization, it requires fit with function. In this, you will start by declaring all the values that you want to work with, which need to be floats in order to work with this particular library. And inside the function itself, you declare everything you want to change. So first we start by creating the learner, chain for X epochs, then save, print, and return the overall accuracy. So this sounds like permutation importance, except it's more guided. Then let's adjust this further to show how we go about adjusting the learning rate, embedded with decay, dropout, and the layer size. So here we check if the number of layers is 2, then go ahead and do 2 layers. If 3, do 3 layers, and otherwise do 1 layer. Then go ahead and build our tabular learner fit for 5 epochs and then return the accuracy. Now let's try it out. Here we define our categorical and continuous variables, the preprocessors, the name of our y's, and we define our y block to be category block. And we will be using random splitter to split our data. Then we define our tabular pandas as we used to do. Call two data loaders with batch size of 512. Now we can declare our hyperparameters in dictionary. For learning rate here is the minimum value and here is the maximum value that we want to search for, and so on for the other parameters. And now we can build our Bayesian optimization. So we pass it our fit function, which is our fit with functions that we declared, our hyperparameters to tune, then we declare the verbose to be 2, whether or not we want it to start at random state. So now we can search, and here is the best results. So what this tells us is the best number of layers was 2. Remember, we are taking the integer values, so we don't care about this part. The first layer size is 57 and the second layer size is 100, and so on for the other parameters. And here it is. So that's it for today's video. Hope you enjoyed.